Hello everyone, Mr. Fawcett here, and we are back with another Algebra 1 lesson. Today we're going to finish up our unit on polynomials and talk about the last type of factoring. And to be honest, the stuff you're going to learn in this lesson, you actually don't need to be able to factor any type of problem, but it's just helpful and can make your life more efficient if you understand the shortcuts we're going to discover in this lesson. So is it anything that's absolutely necessary to factor? No. But again, just like we learned some shortcuts for multiplying binomials, we're going to talk about some shortcuts today that can save you some time when you're working through some problems. So it's always good to be more efficient, and that's what today is about. Okay, so let's skip down here. So it says in lesson 9.4, we looked at how to multiply special cases of binomials. In today's lesson, we're going to look at how to factor special cases of trinomials. And we're actually going to factor some binomials as well, but we'll get there later. So first thing to do is multiply these binomials out. Again, maybe you remember the shortcut. Maybe you need to rewrite these. Right? Remember that this is really equal to x plus 6, that quantity times the quantity x plus 6. And then you could go ahead and distribute. So pause the video, go ahead and do both of those at the top, and then we will continue our discussion. Okay, so I'm just going to put the answers up here. We're not going to walk through how to multiply. You can learn how to do that in a previous lesson. This will give us x squared plus 12x plus 36. Over here, we'd have x squared minus 6x plus 9. So both of these in these boxes, these are called perfect square trinomials. Perfect square trinomials. And this is because the first and the last term are perfect squares. If you're wondering what a perfect square is, well, it's a number that you can take the square root of and get a whole number. So perfect squares are 1, 4, 9, 16, 25, etc. Right? If I take the square root of all these, I will get whole numbers, not decimals or fractions. Right? 1, 2, 3, 4, 5. And of course we could keep on going, right? There's an infinite amount of perfect squares. You may think, well, what about the first term? Right? I understand that the last term here, 9 and 36, those are perfect squares. But x squared, is that a perfect square? Well, if I take the square root of x squared, that just gives me x. Some other examples that include a variable would be something like 4x squared. Use different color. 4x squared. Right? If I take the square root of this will just give me 2x. Maybe I have something like 9x to the 4th. If I take the square root, I'll get 3x squared. So if your first and last term are perfect squares, and the middle term is twice the product of the square roots of the first and last terms, then you have a perfect square trinomial. So let's just break this down one more time. Make sure we understand what a perfect square trinomial is. Let's use this pink example over here. So if we look at the first and last term, perfect square, perfect square. Now for the entire trinomial to be a perfect square, this middle term has to be twice, so 2, times the product of the square root of the first term and the square root of the second term. Well, the square root of the first term is x. The square root of the second term is 6. I'm going to write the 6 in front. So 6 times x times 2 gives me 12x. If I look over here, the first term is x squared. That's a perfect square. 9 is my last term. That's also a perfect square. Now, 6x is twice the product of the square root of 9, which is 3, and the square root of x, which is x. 2 times 3x is 6x. Now, it doesn't matter whether it's a positive or negative sign. Either way, we can make this, either way it would work. It would be a perfect square trinomial. All right, let's just get some practice identifying what are perfect square trinomials, which versus which ones are not. So you have 6 here to look at. Circle the ones you think that are, based on the definition we came up with above. Okay, so hopefully you paused the video, you attempted that. Turns out that, oops, I'm just going to circle them. This one is. This one is. This one is. And that's it. The other ones are not. So let's break down why they are. Both of these are perfect squares. Square root of x squared is x. Square root of 25 is 5. 2 times the square root of 25 and the square root of x squared, that does give us 10x. If I look down at this one below, perfect square, middle term. If I look at the 4, the square root of 2 is, square root of 4 is 2. The square root of 9x squared is 3x. So if I multiply all those together, I do get 12x. Remember, it doesn't matter what the sign is. And we'll talk a little bit about why down below. But as long as we have that 12x, we're good, and we do. Finally, let's do this one in blue. 16x squared is a perfect square, because I just get 4x. 1 is a perfect square, because square root of 1 is just 1. Do I get 8x? Well, 2 times the square root of 1 times the square root of 16x squared, which is 4x. That does indeed give me 8x, so we are good. And you could think about, let's just look at one of these other ones and show why they don't work. If I look at, actually we'll do 2 of them. Let's look at this one right here. Perfect square, but 2 times the square root of 16, which is 4, times the square root of x squared, which is x. That does not give us 10x. Right? It gives us 8x, so it does not work. Over here, we'll do this one in purple. Right off the bat, this is not a perfect square, right? Because the square root of 2 is not a whole number, right? Square root of 2 is irrational. So no good, no good, no good. The other 3 are good. All right. Let's talk about how we can factor these. All right, so if we look at these 2 examples at the bottom of this page, so we're looking at these 2. If we can identify that a trinomial is a perfect square trinomial, then it factors into a recognizable pattern. I'm just going to set up what our factors are going to look like, and then we will fill them in. So eventually, we will see that they both factor into the same binomial squared, just like perfect squares do, right? So 1 is equal to 1 times 1, which is equal to 1 squared. 4 is equal to 2 times 2, which is equal to 2 squared. 9 is equal to 3 times 3, which is equal to 3 squared, and so forth. So the factors of a perfect square trinomial are going to be the same, which means we can write them as one binomial squared. Now the way we figure out those factors is we take the square root of the first term. Let's do this in the same color. Square root of the first term, which is just x. Square root of the last term, which is 4. 16 square root of 16 is 4. So we have x plus 4 times a quantity x plus 4, which means we can just write it as x plus 4 quantity squared. So this would be the factorization for a perfect square trinomial. Now, if we look at the pink, Process is going to be the same except for one thing. Well, we're still taking the square root of the first term. In this case, it's 3x, because we have that 9 we have to take the square root of as well. Square root of the last term is 2. Square root of 4 is 2. Now, we need this negative 12x to be negative. Well, the only way that's going to occur is if we put a negative sign in front of those two terms. So we end up getting the quantity 3x minus 2 squared. And that is our factorization. If the middle term is positive, the sign you're going to use is going to be addition. If the middle term is negative, the sign you're going to use is negative or minus. Let's practice a couple before we move on to the second part of this lesson. Let's do 1 and 4. 1 and 4. Both of those are perfect square trinomials, so just practice factoring them. So pause the video, factor, and then see if you get the correct answer. Okay, so for number 1, the square root of v squared is v. Square root of 9 is 3. And my sign is going to be negative because I'm looking at negative 6v. So I'm going to get the quantity v minus 3 squared. That is my factorization. And you could test it to make sure it's correct, right? You could just multiply those binomials together to see if you get what you started with. If I go down here to number 4, square root of 9n squared is 3n. Square root of 25 is 5. And my sign is going to be positive or addition, because I'm looking at a positive 30n. So I get 3n plus 5 quantity squared would be my final answer. So that's the first little shortcut. Now I can't stress this enough, right? You could have factored these using either the factor sum chart or the AC method. Both of those would work. And if you ever are unsure of whether it's time to use a shortcut, don't guess. Don't say, I think it's time to use a shortcut, so I'm going to use it. Just go back and use one of your reliable methods, right? If I'm looking at pink, let's just make a factor sum chart, right? I'm going to look for factors of 9 that add to negative 6. And I wrote that opposite. Factors of 9 that add or sum to negative 6. So I get 3, negative 3, and negative 3. And you can see that's how we would get these factors here. V minus 3 times the quantity v minus 3. So you can always go back and rely on your factor sum chart or the AC method, or maybe a GCF followed by one of those two if you're unsure of whether a shortcut is able to be used. Let's go back and look at the second possible shortcut though. So go ahead and multiply these binomials together. Although let me switch this one. It's switched on your paper, but not mine. And when you multiply them together, see if you get a trinomial or see if you get something else, right? Normally we get trinomials when we multiply the binomials together, but let's see if that ends up being the case here. Okay, I'm going to go through the steps here because I think you need to see what's going on. So I'm going to get x squared plus 1x, or just x. And then I'm going to get minus 1x minus 1. So when I simplify here, I get x squared. These x terms simplify out, so I get x squared minus 1. So I actually just end up with a binomial here rather than a trinomial. And the same thing happens over here. I'm going to get x squared plus 4x minus 4x minus 16. So I get x squared minus 16. Both of these answers are called the difference of squares. Difference of squares. And the difference implying subtraction. So we're always going to be subtracting two terms here. And squares, meaning both of the terms will be perfect squares. X squared is a perfect square, 1 is a perfect square. X squared is a perfect square, 16 is a perfect square. So again, this is a binomial where both terms are perfect. Whoops. Perfect squares. So now we're going to think about, okay, what if I started with the difference of squares? What if I started with what I boxed and tried to go the other way and tried to factor it? Well, maybe there's some shortcuts here. But again, the first thing we want to do is we want to be able to identify what the difference of squares looks like. So again, the difference of squares, the first term and the second term are both perfect squares, and there's got to be a negative sign in between, or a subtraction sign, or a minus sign. So let's just identify. Let's look at these 6. Circle the ones that are the difference of two squares. If they're not, think about why they're not. Okay, so there's actually some leeway here. Some of you may have circled 1, others may have circled, or others may not have circled it, but you can make a case either way. Definitely, though, we should have circled the first one. X squared is a perfect square, 25 is a perfect square. The second one is no good because it has a plus sign here, right? It needs a minus sign. Same thing for this one, plus sign instead of minus sign. This one we're good. 49 is a perfect square, c squared is a perfect square. This one we are also good. If I take the square root of 4x squared, I would get 2x. Square root of 4x squared is equal to 2x. And the square root of 81 obviously is just 9. Now this one right here is the one there could be some debate on. If we take it just as it is not the difference of two squares. Because the square root of 2, right, is not a whole number. The square root of 32 is not a whole number. However, you could factor out a 2 from both terms to get 2 times the quantity x squared minus 16. Then we do have a perfect square inside the parentheses. So if we take it at face value, no, it's not a perfect square. But if we factor out the greatest common factor, we can turn it into a perfect square. Or sorry, the difference of squares. I'm saying perfect square, I should be saying the difference of squares. All right, let's talk about how to factor these. First thing I want you to know is that just like I said with our previous shortcut, you don't have to use the shortcut, right? If you look at this and you're like, I don't know how to do this, I don't remember the shortcut, you're not out of luck. You can factor this using one of our other methods. If I look at this one, we could factor it using the factor sum chart. The only thing you have to do is you should probably add in the middle term, which is 0x. There are no x's here, so you just put a 0x. It doesn't change anything. Then, when you do your factor sum chart, well, factors of negative 64, that's sum to 0. I get negative 8 and positive 8. So my factors would be x minus 8 times the quantity x plus 8. So no shortcut was used there, right? We just did it the old-fashioned way. But sometimes the old-fashioned way is what we need to use if we forget the new way, the new efficient way. So let's say, we want to try to remember the shortcut. Well, how would we do it? Well, if we think about the pattern up above, we are going to have two sets of parentheses. We're going to take the square root of our first term, which is x, the square root of our last term, which is 8, and we're just going to have opposite signs. One's going to be positive, one's going to be negative. Works the same way over here. The square root of 9x squared is 3x. Square root of 100 is 10. And we have opposite signs. So, again, if you remember this shortcut, it may save you a bit of time. But if you don't, that's okay. You can always go back and try one of our other factoring methods. We are going to do some practice. Let's just take a look at this page real quick. This just kind of breaks down the two different factoring techniques, the two shortcuts. So factoring a perfect square trinomial and factoring the difference of two squares. Let's do number 2 and number 4. We'll end with those today. As always, pause the video, try these on your own, and then come back, check your answers, and see if you did them correctly. Okay, so for number 2, the square root of 4n squared is 2n. The square root of 1 is just 1. And we have opposite signs. For number 3, the square root of 25p squared is 5p. The square root of 9 is 3, and opposite signs. Notice I did the negative sign first this time. That's okay. It doesn't matter what order you do it in. The answer is still going to be correct. All right, that is going to do it for today's lesson. Again, you may not recognize these shortcuts right away, or at least, over the next day or two because they're new to you. But eventually, you'll just pick up on these patterns and you'll say, hey, I can use a shortcut here. Hey, I can use, the difference of squares shortcut here, the perfect square trinomial shortcut here. But never guess. If you're ever unsure of whether a shortcut is allowed, always just go back and do it the long way. It may take you a little bit longer, but at least you'll know that you have the right answer rather than just taking a guess. All right, as always, enjoy the rest of your day, and we will look forward to seeing you next time with a brand new unit.